Okay, should be good. So, hello
All
everyone.
right, thank you.
Welcome. I hope everyone enjoyed their summer vacation to the best of their abilities. So, my name's Ben Stabina. I just finished a 16-month co-op at Stackpole, and I'm going into my final year at Materials. I'm one of the VP academics on the society this year, and one of the roles of the academic team is to create and organize events tailored for the academic success of our students. Hence, why we have this event. So the society is aware that the 1P10 course in the iBiomed does not cover all the materials content from 1MO3. So therefore, this event is aimed to help fill these gaps as well as provide a general refresher of the materials content. So thank you for taking the time to attend the event. I'll be passing the leadership to our department chair, Dr. Zarab, and he'll guide you through the content.
Okay, good afternoon, everyone. And let me echo what Ben just said. Welcome again. I hope you had a great summer. And really, I have been looking forward to seeing students again and to interacting with you again. So I'm so happy that we have a chance today to go over some material that I hope you will find useful. And feel free to stop me at any time. Feel free to tell me if you find that this topic is something you're familiar with and you would rather spend the time on another topic. I have all of my notes ready. We can switch between topics and look after the topics that you need the most help with. And maybe just before we get into some of the review, I just want to be reassuring. Don't feel worried if all of this stuff sounds new or if you haven't seen it before, or even if you can't absorb everything we talked about today. I've talked to all the second year instructors and they all have a reasonable expectation of the knowledge that you have coming out of first year, and they all intend to go over all the necessary background in their courses. So hopefully by attending the session today, you are in a position to impress them and you know right away what they're talking about, and you'll be the one answering all the questions. Sounds good? Are we good to start then? Okay. So I will share my screen and we'll get going, but feel free, as I said, to stop me as many times as you need to. So hopefully you can see my PowerPoint screen. And what I'm working on, what I would like to start with, I understand from Sophie, one of the topics that you wanted to go over was the topic of phase transformations and phase diagrams. So I put some slides together and I'll only focus on the basics, the things that we really need to know. And I think let's start with the basic idea of what is a phase. And we know the phases of matter. We know a phase could be liquid water is a phase, solid ice is another phase, the vapor or the gas is a third phase. So we more or less already know what a phase is. The new aspect here is that usually we thought about pure phases. We thought about pure water. So you can have pure liquid water. And now we're going to think about more complicated systems where multiple elements or multiple components mix together to make a phase. So if I take water and alcohol and I mix them together, I get a new liquid, which is not water, it's not alcohol, it's actually a mixture of water and alcohol. So that's a liquid phase. It's a phase, right? Because the water and the alcohol mix together to make the liquid. So we still have a liquid phase, but that phase is neither pure water nor pure alcohol. It's a solution, a liquid solution of water and alcohol. So that would be an example where we have two components, the water and the alcohol. Those are the two things I'm mixing together, and one phase, the liquid phase. So I put together here a little table just so we can make sure we understand what a phase is and what a component is. So let's start here. The example I just gave, pure water. There is one component. The component is H2O. and the phase is the liquid. So you have one component and one phase. If I was looking at diamond, again, I have one component. That component is carbon. And what's the phase? The phase is the diamond. The crystal structure of diamond defines the phase. Does that make sense? So what's an example where I have two phases and one component? So two phases, you have ice water. If I have a cup of water with ice in it, I have two phases, the ice, the solid, and the liquid water. So two phases, but in fact one component, one chemical is involved in this, it's H2O. Okay, what about this one here? Two components and one phase. Well, if I mix water and ethanol together, two components, H2O and ethanol, but one phase, a single liquid solution. Another example is if I bring copper and zinc and I alloy them together, they make an alloy called brass. So brass, if you look at it, you can't make out copper atoms and zinc atoms. You can't separate them. They're completely mixed together. So there is only one phase, which is the brass phase, even though we have two elements or two components that have been mixed together. Now, if I mix two things and those things did not end up completely dissolving one another, like water and salt, if I put too much salt into water, I'll have the liquid and some undissolved salt at the bottom. So that will be an example where I have two components, the water and the salt, and two phases, the liquid and the solid. So two phases and two components. And then you could go as many components as you want. You can make complicated phases and so on. But that's the basic idea. That's what I mean by a phase and a component. So I'm going to show you now a simple example of a phase diagram. A phase diagram basically tells us what to expect when we mix two elements or two compounds together. So in my example here, it's a hypothetical example. I'm looking at what happens when I mix element A and element B together. And I'm looking at the outcome as a function of temperature. So the ends of this diagram, here and here, are the pure material. Over here, I have pure A, and over here, I have pure B. If I look at pure A, it seems that A, in its pure form, is a solid up to 600 degrees C, and then it melts above 600 and becomes a liquid. And if I look at B, it looks like B is a solid all the way up to almost 1300 degrees, and then it becomes a liquid. So this you would have, for example, found out simply by looking at your periodic table. If you knew what element A was and what element B was, you would know what their melting points are. That's not complicated. Where a phase diagram comes in handy is when you mix the two. What is the melting point of an alloy or a mixture of 50% A, 50% B? What's the melting point if it's 20% A and 80% B? That gets more tricky. And that's why you need the phase diagram. The phase diagram answers this question for you. So if I take the example here, what happens if I put 40% B, okay, so 40% B, which means I have 60% A, because I'm looking at a binary mixture, only A and B. So if I put 40% B, there must be 60% A. So if I mix those two together, the phase diagram tells me that at 300 degrees, for example, over here, I have just a solid phase. A and B will completely dissolve each other and form a single solid phase, or in other words, a solid solution or an alloy of A and B. And that alloy, 40% of its atoms will be B atoms and 60% of its atoms will be A atoms. If I keep increasing the temperature, I'm still dealing with a solid, until I get to this line here. This black line that I just touched now is called the solidus. So I'll write that down. This line here is called the solidus. It's the line at which an alloy begins to melt. So once we enter into this region here between the solid and the liquid, this region is actually a region where you have both solid and liquid. So once I cross this dark line or this black line, some liquid begins to form within my alloy. And you can imagine as we go higher and higher in temperature, there will be more and more liquid and less solid until we get to this point here. So this second black line is called the liquidus. And once we exceed the temperature of the liquidus, we have 100% liquid. So once I'm anywhere here, everything is liquid again. Does that make sense? So the phase diagram is telling us for different alloys, anything from pure A to pure B, anything in between, what to expect at different temperatures. Are we going to have a solid, a liquid, a solid, and a liquid? So let's look at an example of how this knowledge is used or how it's applied. So suppose I picked a point in here, this blue point. So we know that this blue point corresponds to an alloy which is 40% B being held at 900 degrees C. Okay, so that's something I have to tell you. I am interested in an alloy of 40% B and 60% A. That's how you know to look at the 40%. And I also have to tell you at what temperature, and let's say I said I'm interested at 900 degrees. So 900 and 40% position me at this point here, the red point here, which is inside the solid plus liquid region. So the first piece of information you can tell me about this system is that it consists of solid plus liquid. That's the first thing we know. Does that make sense? The second thing we want to know perhaps is, okay, you have a solid and you have a liquid. Now, is the solid 40% B and 60% A? What about the liquid? Is it 40% B and 60% A? And it turns out the answer is no. Neither the solid nor the liquid has the same composition as the overall composition. The way we find their compositions is, remember, this side here is the liquid, this side here is the solid. So what you need to do if you want to find out the composition of the liquid, or if you want to know what is that liquid made of, is to go horizontally until you get to the liquid side and then read the value. So if I do that, I realize that whereas I mixed overall 40% B and 60% A, once I heat it to 900 degrees, and once this material formed a mixture of liquid and solid, the liquid is 20% B, and of course 80% A. On the other hand, the solid, if we go to the other side, if I read the values here, the solid is 70% B. So the solid is rich in B. It has 70% B and only 30% A. So the point we have to realize here is we have two phases, solid and liquid. Each one of those phases has a different composition. It has a different makeup. The solid is 70% B. The liquid, on the other hand, is 20% B. Now, very often people ask, should these two compositions add up to 100%? So, for example, 20% B here and 70% B here, should they add up to 100%? The answer is no, because the composition of the liquid is the liquid's business. The composition of the solid is the solid's composition. They shouldn't have nothing to do with each other. The only thing you have to check for consistency, if you have 20% B in the liquid, it means there is 80% A. You have 70% B in the solid, okay, that means you have 30% A in the solid. But the B in the solid and the B in the liquid are not related. They need not add to 100%. Are we happy? So far, so good? Okay. So we know we have two phases, the liquid and the solid, and we know the composition of the liquid and the composition of the solid. So I just want to write this down. These things here are called compositions. Okay, next I'm going to look at the amounts. So now I'm curious, if I'm imagining this cup or crucible that has liquid and solid in it, I would like to know, is there a lot of liquid and so little solid? Is it mostly liquid? Or is it mostly solid? Or maybe half of it is liquid, half of it is solid? Really, I want to know what is the amount of the liquid and what's the amount of the solid. And it turns out there's an easy way to find out the amounts. This way is called the lever rule. The way the lever rule works is, again, you sketch that horizontal line that connects the solid and the liquid. It has to go through the point that we're interested in. We said we're interested in this point. So I'll draw a line through this point that connects the liquid and the solid. What I need to do next is to say which phase am I interested in? Am I interested in the amount of solid or the amount of liquid? So let's say I'm interested in the amount of solid. So solid is here. It's this side here. So the lever rule might seem counterintuitive. What it asks you to do is, if you want the amount of solid, which is over here, you take this distance here. You take the distance from the overall composition to the liquid, this distance. Okay, let's call this distance x. You take x and you divide it by the total distance between the solid and the liquid. You divide it by this total distance. So if that total distance is y, we do x over y. That would be the amount of solid. So in our example here, x, the distance from 40% to 20%, is 20. And then the total length of this tie line, this long line from here to here, that total distance is the difference between 70 and 20. So that's 50, which makes me conclude that this material is 40% solid. So this material is 40% solid, and obviously, if it's 40% solid, what's the rest? The rest is liquid, so 60% liquid. so we see that here in my calculation, we get the 40% solid. Coarse, 60% liquid. Now, does that answer make sense? Did we expect that answer? And I would say, yes, it's not unexpected. The answer makes sense. And the reason the answer makes sense is that the point we're interested in okay, how do I get rid of my eraser now? Okay, here we go. The point I'm interested in, this one here, is actually closer to the liquid. Over here is 100% liquid. This point is closer to 100% liquid. So it makes sense that it has more liquid than solid. Does that make sense? Whereas if I look at the next example we have here, if I take this point instead, so if I gave you a different alloy and said, why don't we put 60% B and 40% A, of course, and hold at 900 degrees. So we're interested in this blue point over here. We know again that we will have solid plus liquid because we are in this middle region. Interestingly, the composition of the liquid has not changed, it's 20%. The composition of the solid has not changed, it's 70%. And I got those just by drawing a horizontal line here. But the amounts of the two phases changed. There is now more solid in this cup or this crucible, and the reason I know there is more solid is this point has now moved closer to 100% solid. And I can calculate the amount of solid. Remember, always take the opposite side of the lever. Solid is here, so take this distance. So the amount of solid is equal to 60 minus 20 divided by the total length of the lever. And the total length of the lever is 70 minus 20. So we now have 40 over 50. So the material is now 80% solid. And of course, 20% liquid. Does that make sense? Are we happy with this explanation? Is it okay? Good, good. All right, thank you. So basically, that's it. That's what you need for phase diagrams. Those simple ideas. What phase do we have? What is the composition of the phase? And what's the amount of the phase? These are the only three things anyone can ask you about a phase diagram. And you wonder sometimes, why is that topic difficult or why can it be confusing? In fact, it doesn't need to be. The reason we often feel intimidated by phase diagrams is very often the phase diagram can be complicated, like this one here. It might have many phases, it might have many components, and it might look complex. But once you know what the temperature is, and once you know what the composition is, you can find a point on the diagram. And once you found a point on the diagram, just look at that point, ignore everything else, and apply the rules to that point. And it's absolutely no different from the example we did before. So I'll show you that in a minute, but that's it. You now know everything there is to know about those binary phase diagrams. So in this example here, I'm just showing you an example of a more complicated phase diagram, and it's only more complicated because it looks more complicated. The concepts are exactly the same. So in this example here, again, I'm mixing A and B. And notice how in the liquid, A and B mix completely. I can put any amount of A and B and heat it to a high enough temperature to make one liquid, which is a homogeneous liquid solution of A and B. But interestingly, in the solid, A and B do not always mix. Let's take an example. If this is A, this is pure A over here. I can put a little bit of B inside A. For example, if I have this composition here, 5% B, 5% B can completely dissolve in A. But if I keep adding B, if I go to this point instead, what happens now? The diagram says you have two phases, alpha and beta. Now, what are alpha and beta? Well, alpha is a solid and beta is another solid. So those two solids would have, for example, different crystal structures. For example, alpha could be FCC and beta could be BCC. And you might ask, well, why didn't we call alpha and beta A, solid A and solid B? The reason we don't call them solid A and solid B and we start using the Greek letters instead is that alpha is almost pure A, but it's not 100% pure A. You can see here that alpha has some width to it. This region is not a straight line. It has some width to it, which means you can put a little bit of B inside A, and the two would mix together. So the solid that they make when they mix together, this A-rich solid is not A, it's alpha. And similarly here, this beta is not pure B. It actually can have a little bit of A. If I go here to the axis, it can have a little bit of A. So it would be wrong of me to call this solid B. It's better to call it beta. So beta reminds you it's rich in B, but it's not pure B. And interestingly here, if I have a mixture like this one here, let's say 30% B and 70% A, you see we'll have a mixture of two solids, not one solid, two different solids, solid alpha and solid beta. So we have two solid phases, alpha and beta. And then that's it. Everything else in this diagram is similar to what we have seen before. If I look here, I have the solid alpha and the liquid. If I look here, I have the solid beta and the liquid. Are we happy with this? Does that make sense? Okay, maybe time for a quiz or a quick question. Can you see, okay, can you give me an example on this diagram where I have only one phase? You can type it in the chat or you can speak up. We only have a few people, so it's okay. Unmute your mic and give me an example of a temperature and percentage of B where we have only one phase.
Like high up and at 50% it's all liquid. So the temperature would be like, I don't know, 900 and the weight would be 50% or something.
Okay, yeah, so if I go 50%, so somewhere here, and the high temperature, my mistake, I did not put an axis for temperature. So if I'm up here, for example, this composition, you're right on, I will have only one phase, and that phase would be the liquid. Very good. What about a place where I have two phases? Well, I gave this away. It's labeled on the diagram. There is this region here, this triangle here. I have two phases. I have alpha and liquid. This triangle here, I have beta and liquid. And in this trapezoid all the way here, this region here, I have two solids, alpha and beta. Now, maybe this is a better diagram. This is the phase diagram for lead and tin, which is the basis for solder. And you notice something curious about these phase diagrams. The melting point of lead is 327. The melting point of tin is 232. But interestingly, if I mix lead and tin in the right amount, so this, it's labeled here 61.9% tin and the balance lead. If I mix them in that amount, I can make a liquid exist all the way down to this temperature here. This temperature is about 180 degrees. So if you want to make a low melting point liquid, one trick is to mix multiple elements. Very often, in this kind of phase diagram, when you mix two elements, the melting point of the mixture is actually lower than the melting points of the individual elements. And that's what people need for soldering electronics. They want a low melting point liquid because this way they won't need to heat up the circuit board and damage it while they're soldering. So we'll answer a few questions for this phase diagram. So the first one was, what are the melting points of lead and tin? Well, this axis is labeled percent tin. So when it's 100% tin, this side here is tin. And when it's 0% tin, this side must be lead. So the melting point of lead is 327. The melting point of tin is 232. How many phases are there in the system? In the system, it means in the whole diagram. How many phases are possible? Well, we have a liquid, we have alpha, we have beta. Everything in this diagram is a combination of those three phases. So the answer here is alpha, beta, liquid. These are the only possibilities. What are the two solid phases? We always give the solid phases the Greek letters, so the solid phases are alpha and beta. And now there is something new. Where is the eutectic point? So there is on this diagram a very special point. That's the point where we get the lowest, that's the lowest temperature at which the liquid exists. So we were talking about this before. This here is the eutectic point. The temperature corresponding to that point is called T eutectic, the eutectic temperature. And the composition corresponding to that point is called the eutectic composition. And notice the eutectic point is special because at that point, three phases meet. Three phases are in equilibrium. We have the liquid, which touches the point from the top here. We have the alpha, which touches the point on this side here. And we have the beta, which exists on this side here. So in fact, anywhere along this line here, you will have three phases in coexistence, alpha, liquid, and beta. Those three phases will coexist along the eutectic line. And that's why this kind of phase diagram is referred to as a eutectic phase diagram. Are we happy? So far, so good? So phase diagrams, not so bad? Are we good to go with an example then? Okay, I won't give you the answers right away, so you have to try them first and maybe type your answers in the chat, and I'll keep an eye on that, and then I'll step in. So part A, it says we have 30% tin, so that tells me somewhere along this line. And the temperature is 200 degrees, 150, so there are multiple questions here, and 75. So for each one of those temperatures, tell me what phases will we have. So 30% and 200, what phases do we have? Yes, Elif, you got it right. So that's alpha and liquid, perfect. Okay, for 200, we got that, alpha and liquid. And for, what about for 150? That would be this point here. Great, okay, Maymoon, that's good. Alpha and beta, perfect, as we see here. And what about at 75 degrees? So somewhere here, the same thing, perfect. Thanks, Nilsu. So that will be alpha and beta again. Sounds good? So that part of the question is easy, you got it. You know, regardless of where we are on this phase diagram, what phases are present. Okay, so part B. For the same alloy, determine the weight fractions of each phase. So for the same 3 points we're talking about, what are the weight fractions of the phases? And before we rush, remember, what is the question asking? The weight fraction of the phases. What is it asking you for? Is it asking you for the composition of the phase or the amount of the phase? Yeah, it's asking for the amount. It wants to know how much liquid is there and how much solid is there. All right, is that mixture going to be all liquid, or a liquid with a little bit of solid, or maybe mainly solid? Or if we have alpha and beta, is it mainly alpha? Is it mainly beta? How much of each do we have? So do we understand the question? Okay, I'll give you a hint. Every time it asks you about the amount, we're going to use the lever rule. So why don't you get started with 200 degrees, use the lever rule, and try to estimate how much alpha and how much liquid we're going to have. So again, we'll start with the 200 degrees question. So for 200 degrees, we're going to use the lever rule and figure out the amount of alpha and the amount of liquid. Yeah, go ahead.
Sorry, I just can't see towards the right of the 200 degrees point. Does it touch the Liquidus at like 55%? I just can't tell. I want to use the right.
It's a little bit hard to read the exact values. So over here, let's see. Yeah, what we're going to guesstimate for this question. So let's say it is 55. Yeah, so this is 50. This is 55. And I'm guessing this one is probably close to 18%. So let's put 18 here.
So I think it's around 32% alpha, and then it would be the rest liquid, I believe.
Okay, you did the math right. We just have to decide on one thing. So this alloy is located at this point here, or the condition we're interested in is this point here. Now, is this point closer to the alpha side or the liquid side? And we see it's closer to the alpha side, right? The closer I get to the alpha side, the more alpha I should have. So you calculated 32%. Is the 32% the amount of the liquid, or is it the amount of the alpha? And the way you can decide is, I'm closer, this point is closer to alpha, so it should have more alpha than 50% and less liquid than 50%. Does that make sense?
Yes, it does. Yeah, thank you.
So that, and in fact, I like to calculate on a test or an exam quickly. So I just do one of the levers without thinking which phase it is I'm calculating. And then I ask myself, well, looks like I'm closer to alpha, so what I calculated must be, the 32% must be the liquid. Because the liquid is here, and I'm far away from the liquid, so I have less than 50% liquid. So this will be the alpha and the liquid. So the liquid will be 32%. And the alpha is actually the majority. It should be 68%, right? That adds up to 100. Does that make sense? Do we like that? I see in the chat, yeah, 40% alpha, 60% beta. Yeah, okay, so that must be for the next one. Okay, so is that for 150? 40% alpha, 60% beta? Let's have a look. So if we're doing 150, I am in the alpha plus beta. Now notice how this point is close to alpha, really far away from beta. So I'm expecting a lot of alpha and not so much beta. So remember, if I want the amount of alpha, this is alpha here, I would take this side of the lever divided by the total. So it's actually probably even more than 60%. I have a slide for that. Let's just scroll down to the slide.
I think I did my math wrong, my bad.
No, you didn't do anything wrong. I mean, the answers I'm showing here are actually not the answers to this question. These are the compositions of the phases, not the amounts. So I'll just, here we go. You're very close. Actually, this is the one with the amounts. So 33% liquid and 67% alpha. So you were right on, in fact. That's good. And then for 150, we would take, for the alpha, we would take this distance divided by the total of the blue line. So it's about, if we do that, it's 30 minus, this is 10, divided by the total. The total runs from here to here, 98 minus 10. So it's about 20 over 88. And if you do the math, that's 23%. So I am taking this distance. So this distance means I'm calculating the amount of the beta, right? Beta is here. This distance always gives you the far away phase, so the beta. So there is only 23% beta, and the amount of alpha is the rest. Or if you wanted to calculate right from the beginning the amount of the alpha, you would take this distance, the part of the blue line that's far away from alpha, so take this side over the total, and that will give you the amount of the alpha. Are we happy with this? So always, the way you can remember it is just do a sanity check. If this point kept moving closer and closer and closer and closer to the alpha, what should happen? I should get 100% alpha, right? So the closer I get to the alpha side, the more alpha I should have. The only way you can get that conclusion is by taking the side of the lever which is away from alpha, by taking this side here. You agree? Okay, so assuming you agreed, let's see if we can get, if you can get the one for 75 degrees correctly. Can we get the amounts of the phases correctly at 75 degrees? So once you get it, add that to the chat and we'll have a look. Don't be shy, it's completely okay to get it wrong. Just think about it. If I want the amount of alpha, alpha is here, right? This is alpha. I take the far away side of the lever, so this side here. So that's about 98 minus 30. and I divide it by the total length of the lever, which is 98 minus, let's say 5, and that gives me the amount of alpha as 73%. And if it's 73% alpha, what's the rest? The rest is beta. Oh yeah, 71 is perfect, Maymoon. That's good. Yeah, 71% alpha is right on. Yeah, so it's just difficult to read the exact values on the screen. That's pretty good. Are we happy with this? So we got the idea of the amounts of the phases and what phases are present and so on. So just for the sake of completeness, in this example here, we concluded there is 73% alpha and 27% beta. Suppose I was curious, what is the composition of the alpha? What is the alpha made of? That one is really easy. The amount of, what is the alpha made of? All you need to do is just draw a line and read the value. So it looks like the alpha is 5% tin, 98% lead. So alpha is not pure lead, but it's almost. It's 95% lead and only 5% tin. The beta is 98% tin and only 2% lead. So very high tin concentration in the beta. Are we still going strong? Okay, I mean, here's a nice diagram. Just it gives you a nice simple explanation of something you've noticed before. Why do we spread salt on the roads during the winter? And the reason is ice on its own melts at 0 degrees C. When you mix ice and sodium chloride, you get a eutectic. And you'll notice this axis here is the concentration of sodium chloride. As I add more and more sodium chloride, the melting point of the ice decreases. So if I spread 10% salt on the road, at -5 degrees, the mixture of H2O and NaCl would be a liquid. It will be brine, so it will melt the ice. The best we can do, if you buy the salt, you sometimes would see on it, it will say good down to -20, and another one will say up to -40. Well, it depends on what the salt is. If it's rock salt or sodium chloride, you can see from the diagram, the best you can do, the lowest temperature at which you can have a liquid by mixing salt and ice is -21. If the temperature is really cold, let's say if we had a day with -30, the phase diagram says you have ice and salt. So you will spread the salt on the driveway and it will do nothing. It will just sit on top of the ice because the phase diagram says at -30, there is no liquid phase. You will have salt and ice. But if it was a little bit warmer, if it was -15, for example, then when you put a little bit of salt, you will have ice and liquid. It will turn into a slushy mix. And if you keep adding more and more salt, assuming you add at least, 18% salt, you could turn it into a liquid. It will be completely liquid. If you keep adding salt, you're just wasting your money, because if you add too much salt, the salt will just sit there. You'll have salt and brine. The salt is no longer doing anything good for you.
Just a question. I'm kind of interested. What do they add to the salt that is good down to -40 degrees? Like, what kind of changes do they make to it?
Yeah, it will just be a different salt. So instead of sodium chloride, it might be another ionic compound. I haven't honestly looked at it. It might be some calcium compound. So the tricky part is to find an ionic compound that depresses the melting point, but at the same time is not so bad for the environment, because eventually it will go on your grass, it will go to the lake, and Even sodium chloride, as harmless as it is, it's actually very bad for the environment because we're basically dumping salt into our waterways. So that's the tricky part of trying to find a good salt to use to melt the ice. All right, are we happy? That's good. All right, so I understand another topic you were interested in is phase transformations. I can try to explain that in 5-10 minutes if you're interested. Should I go for it? Okay. So what do we mean by a phase transformation? It's nothing fancy. Let's say I have liquid water at 5 degrees C. The starting state is liquid. And now I begin to cool it down to -5 degrees. The final state is solid. So there will be a phase transformation, a change of phase from liquid to solid. That's it. That's what we mean by a phase transformation. What we're interested in is how fast is that phase transformation going to happen? And you know intuitively, the more you cool the water, the faster it will freeze. If you just hold the water at -1 degree, it might take a long time for it to freeze. If you put it in a deep freezer at -20 or -40, it might freeze more quickly. So we call that the kinetics. How fast does something happen? And we can actually make a diagram to show how quickly something happens. So my x-axis here is time. It's not heating time, this is called holding time. So how long I have put that water cup in the freezer. And this here is the fraction transformed. How much of the liquid water has frozen and turned into ice. So obviously at time 0, just take that liquid water, initially at room temperature, I open the freezer, I put it in and I close it. Initially, I have 100% liquid. And what you find is there is an incubation time, there is a delay. It doesn't start freezing immediately. Some time will pass. If you open the freezer and took it out after 5 minutes, you'll find it's still completely liquid. You put it back in, and maybe after 30 minutes, you find it's beginning to freeze. It's slushy now. Some water, some liquid. So pretend you had an easy way of measuring the amounts. You can put it on your diagram. So after 20 minutes, I found 20% solid. After 70 minutes, it was 50% solid, and after 2 hours, it was 100% solid. So this curve here shows us the kinetics, or how fast the phase transformation happens, and it can be described by a simple equation, and there is nothing fancy about this equation. It's just the math. It's the simplest mathematical expression that goes from 0 to 1 with time. We want something that starts as 0 and goes to 1 at long time. I mean, you can try the numbers. If I make t equals 0, that becomes the exponential of 0, which is 1. 1 minus 1 is 0. So at time t equals 0, the fraction transformed is 0. Well, what happens when t goes to very long times, let's say infinity? This becomes the exponential of minus infinity. So the exponential of minus infinity is 0. 1 minus 0 is 1. So the whole thing here is just an equation that would give us the transformation from the beginning to the end. So now let's pretend we're doing a different phase transformation. Let's imagine this material, which is FCC at high temperature and BCC at low temperatures. And the transformation temperature from FCC to BCC is 700 degrees. So above 700 degrees, I can wait forever. It will stay FCC. Below 700 degrees, I know that after some time, it will transform to BCC. The question is, how quickly? So suppose someone did the experiment, and at 690, they measured this curve here. So they found that after 10 seconds, the transformation begins. It really takes off, and at around 500 seconds is finished. There is a lot of information here in this diagram, but I'm going to take only one piece of information from this diagram and put it on this second diagram here. So this second diagram shows me for a given temperature, 690, how long did it take for the transformation to be 50% complete? So 50% complete is around here. So it looks like it took 300 seconds. So I'm going to go to this diagram here and put 690 and 300 seconds. That's my point. So this temperature gave me 1 point on the diagram. Now I'm going to ask, okay, 690, the reaction is half complete within 300 seconds. What happens at 600 degrees? And just like the example with the water, the more you cool the water below 0 degrees, the faster it freezes. So the same thing here, the more I cool this material below the equilibrium point, so the equilibrium point is 700 degrees, the more I go below 700, the more and more likely this material is to transform to BCC, and the faster this will happen. So we see on the diagram here that the whole thing is now done within 10 seconds. I can put that piece of information on my diagram here. So 50% transformation took about 2, 3, 4, 5, 6 seconds. So I'll put that here, 600 degrees and 6 seconds over here. And I can do this for, again, one more temperature. Let's go to an even lower temperature, 500 degrees, and we get another curve. And you might be surprised now, wait a minute, I cooled it even more, right? That's like taking liquid water down to minus 200 degrees. And I'm saying in this example here, where FCC goes to BCC, rather than the transformation happening more quickly, it actually slows down. It slowed down compared to the 600. 600 was finished within 10 seconds. 500 is taking almost 100 seconds. So why is that solid-solid transformation different from the freezing of water? The reason it's different is that there is a lot of atomic movement needed for the FCC atoms to rearrange into BCC atoms, right? They have to move around within the solid. And atomic movement in the solid is difficult. It's not like atomic movement in the liquid, right? So we call this diffusion. Diffusion in the solids is slow. It requires activation energy. It requires heat for those atoms to be able to break their bonds, move, and make new bonds. And what seems to happen in my example here is when I went to 500 degrees, even though there is a huge driving force, there is a big incentive for FCC to change into BCC, excuse me, because we're at such a low temperature compared to where FCC should exist. FCC is only supposed to be there above 700 degrees. So now I'm a full 200 degrees below that. That FCC should be gone. But the reason it's taking a long time to go away is that the diffusion is very slow. It's taking a lot of time. The atoms are trying their best, but they just don't have the energy. They're just moving as fast as they could, and it's taking them a long time. So if I add that point to the diagram, you see it took longer time at 500. And if I connect the points, or if I do a lot of experiments, I can make a full curve. And this curve here is called a T diagram. The first T is temperature, the second T is time, and the last T is transformation, because it's showing us the time for 50% transformation. Is that okay? So it's a very practical diagram. You can choose any temperature you want, and this diagram will tell you how long will it take for the material to transform. And we often use that to understand the processing of steel. So this is the diagram for iron and carbon, which is the basis for steels. And I'll just quickly mention, it looks complicated, but it's no different from any other phase diagram. This region here is liquid, no surprise. This region here is gamma, and it has a nickname because steel has been around for hundreds and hundreds of years, so a lot of the phases have nicknames. So gamma is also known as austenite. So anywhere within this region here is austenite. There's a tiny region here, delta. So delta is another solid. It's actually BCC. Gamma is FCC. And this thin region here is alpha. And alpha has a nickname, ferrite. And the ferrite has a crystal structure, which is BCC. And there's actually one phase that's hard to see. It's this compound, Fe3C. Now it's a compound, so it has a very determined stoichiometry. It doesn't have any width to it. It has to be exactly 25 atom percent. So up here is the atom percent. Here is the weight percent. It's exactly 25% carbon and 75% iron. So it shows up as just a thin line on the diagram. So this thin line is the cementite. There's nothing different about this diagram. Everything else, you use the rules we discussed before. If I'm here, what do I have? I have gamma plus liquid. If I'm here, what do I have? I have two solids, gamma and Fe3C. If I'm here, what do I have? Two other solids, alpha and Fe3C, and so on. The nice thing here is we can look at an example where austenite, let's say, have a steel of composition 0.2, which is heated up here. That's what typically happens during the hot rolling of the steel when they're forming it at high temperature. So it's austenite or gamma, and now I'm cooling it down. And once I get to this temperature here, it should transform to alpha plus Fe3C. So this alpha plus Fe3C has several nicknames. One of them is perlite. If the alpha and Fe3C formed in the form of a colony with alternating layers like that, where you have one layer of Fe3C, that's the red region, then the white is alpha, then another red region, then alpha. See, they're alternating alpha Fe3C, alpha Fe3C. This mixture or that arrangement is referred to as perlite. So you can have austenite decomposing or changing into two solids, the alpha and the Fe3C, which form side by side. We call that perlite. So we have the austenite transforming into perlite, and this diagram is just showing us how the more we cool the austenite, the faster it transforms to perlite. And we can use that information to build a real TTT diagram, temperature, time, transformation diagram, that shows austenite going to perlite. And this diagram is nice. They gave you not only the 50% point like I did in my example, they also showed you a point for the start of the transformation. So just when you have a little bit more than 0%, and a point when the transformation is almost finished as you approach 100%. So that's very nice. Just one diagram tells you when the transformation begins, when it finishes, and if you want, when it's almost done, 50-50. Are we happy with that so far? Or did I go too fast? We're good? All right. So this here is just a schematic of the perlite, maybe a little bit better than my little sketch. This is the alpha, this is the Fe3C. This is the alpha, this is the Fe3C. And that colony grows and replaces the gamma phase. So this is just another schematic. If I start at high temperature, I cool down. If I'm holding for these shorter times, nothing happens. It's still in the gamma region. Once I hit the red line, I begin to make the perlite. At this point, the process is 50% done. So you can see almost half the sample has turned into layers of alpha Fe3C, alpha plus Fe3C. And by the time I got to the green line, everything has transformed into alpha plus Fe3C. And the nice thing about this diagram is if I did this experiment at a different temperature, if instead of doing it at this temperature, 625, if I did that at 550, I know exactly when it will begin and when it will end. So very powerful diagram. It has so much information in it. Now, if we look at even lower temperatures, we find that the curve, as we discussed before, up until here, the transformation is happening faster and faster. And I know that because look up here, it took 10 seconds for the transformation to begin. Around here, it's only 1 second. But if I keep decreasing the temperature, the times begin to increase. So at 400 degrees, the time has become almost 5 seconds. At 350, it's 10 seconds. At 280, it's 100 seconds. The time is getting longer and longer. So that's similar to what we talked about before. And the reason for that is the diffusion is slowing down, so everything is taking longer and longer time. And actually a second thing happens. So here we had these nice alternating layers that we call perlite. In here we have something else called Bainite. So what happens now is the ferrite forms, like you have a blob of ferrite like that, and the cementite will be in the form of tiny needles inside it. So rather than those beautiful lamella, ferrite, cementite, you now have the ferrite with some lamella or tiny needles, discontinuous needles of cementite. I keep saying cementite, old habits. Cementite is the same as Fe3C. So these lamella or needles of Fe3C embedded inside. So still alpha plus Fe3C, but the arrangement is different, so people give it a different name. They called it Bainite. And the last interesting thing to see here is, well, what happens below this temperature here? So suppose I manage to cool my material from high temperature to low temperature so fast that not even a second lapsed before the temperature came down to 200 degrees or to room temperature. So that's what would happen if you took something red hot right out of the furnace and dipped it in water. It cools down within a fraction of a second. So there is no time for diffusion. There is no time to make perlite, the lamella. There is no time to make bainite, the needles. There is no time for any of that. In that case, the only thing that can happen is a transformation that does not require diffusion. So there are transformations that happen that do not require diffusion, that do not require the atoms to jump from their positions. Rather, what happens is we call it a shear. There is a tiny shift in atomic positions that happen. All the atoms move at once, and that shifting changes the crystal structure from one to another related one. So what happens here is the FCC, or the austenite, or in this diagram they also show it as A. So this is A for austenite, okay? Or gamma. It transforms to M, which stands for martensite. And martensite has a different crystal structure that we haven't learned about, but it doesn't matter. It's called BCT, body center tetragonal. But for all we care, it's just another crystal structure. So that shows you that depending on what path you take as you cool the sample down, maybe you make perlite, maybe you make bainite, or maybe you make martensite. And this is just a schematic showing how these different ones look like. The top is perlite, see the alternating lamella. The next two are two kinds of bainite, where you have the ferrite and some needles of Fe3C inside it. And then you have the martensite, which is this very messy structure you see here. This messy structure here, full of dislocations, full of deformation. This is called bainite, martensite. And what makes this all very fascinating is that each one of those has different properties. So by changing your cooling path, you can get different phases and different properties. So you can make coarse pearlite. What I mean by coarse is pearlite where the spacing of the lamella is very large. So coarse pearlite is very, very soft. So you get the material which is ductile and soft, so good for forming, for making complex shapes. If you cool a little bit faster, you get the fine pearlite where the spacing of the lamella in the pearlite is smaller. So this would be stronger than before, but still has good ductility. If you cool even faster, you get something even stronger, the bainite. And if you cool even faster, you get the strongest structure, which is the martensite. But the martensite is also the most brittle structure. So martensite is extremely strong, but it doesn't deform. It snaps, it breaks. And very often, we take that martensite and we heat it up a little bit. This is a process called tempering. And during tempering, we can change the structure of the martensite a little bit to make it softer. Are we happy with this? A quick example, maybe? So this question says, I'm going to give you a TTT diagram, and you're going to tell me what happens if we go to 650 degrees and hold for 30 seconds. So here's the TTT diagram. To use the TTT diagram, you have to always start with gamma. It only works if you started with gamma. So we're going to assume we started at 800 degrees, and at 800 degrees, we start with 100% gamma. Okay? And it says we cool quickly to 650. So I come down, this is 650, and I hold for 30 seconds, and that's my 30 seconds. So at this point, after holding for 30 seconds, what do I have? Well, let's look at the diagram. It says above this line here, we have perlite, or we make perlite. And these lines here tell me how much perlite I've made. So starting here, I begin to make the perlite. By the time I get to this line, I made 50% perlite. So after 30 seconds, I have 50% perlite. And what's the rest of my material? The rest of my material, the other 50%, is gamma or austenite. Now that's not the final answer, because the question says you hold for 30 seconds and then there is a new step. It says then quickly cool to room temperature. And an important thing to remember about these diagrams, every time the question says then, every time there is a subsequent step, go back to 0 time. So I'm now back at 0 because it said then. And then it said then cool down to room temperature. So I'll just go down to room temperature quickly. So notice in that path, I did not touch perlite again. I did not touch bainite again. The only lines I crossed are the start of martensite formation. I crossed 50% martensite, and I crossed 100% martensite. So during the quenching step, I made martensite. Now the important thing to remember is what has transformed to martensite. Does everything transform to martensite? Does the gamma transform to martensite? Yes, it does, right? The gamma is the FCC. It shouldn't be there at room temperature. It should transform to martensite. What about the perlite? Does the perlite transform to martensite? To answer this, let's look at the phase diagram. At room temperature, what phases should we have? So room temperature is somewhere here. So what phases do we have at room temperature? Well, it looks like we should have alpha and Fe3C. So what is alpha and Fe3C? Alpha and Fe3C is essentially our perlite. We said perlite is alpha plus Fe3C. So is the perlite okay to be present at room temperature? Absolutely. It's an equilibrium phase. That's what the phase diagram has, so it should be there. And therefore, it should stay there. Once you make the equilibrium phase, the one that shows up on the phase diagram, it stays there forever. It's supposed to be there. So nothing happens to our perlite. The only thing that changes is our martensite. That is our, the only thing that changed is our gamma or our austenite. It goes to martensite. So the final outcome is 50% perlite and 50% martensite. Does that make sense? Are we happy with this? All right. Any questions about phase diagrams and phase transformations? Maybe I'll stop for a second and take questions. And then I'm aware it's 6:20, so I have time. Don't worry about me, but I know you might have other things. So let's see if you have questions first about phase transformations, phase diagrams, and then we can check if there are other topics you want me to go over. I have a few slides about stress strain curves. I have a few slides about planes and directions, so we can see what you are interested in. So you can type in the chat. I think there is a little bit of a delay between the time you enter things on the chat and the time they show up on my screen. You can also just unmute and let me know. Okay, so I take it there are no questions. That's good.
I actually have one, Dr. Zarab.
Oh, good. Yes, I feel good about it.
So let's say we go back to the original question in which you held for 30 seconds at 650 degrees. Would you like to explain what would happen if we then decided to reheat our sample back to 800 degrees?
Good question. Okay. So in this question here, I should add a detail on this diagram. So let's say on this diagram, there is a line here at 750 that shows the equilibrium. So up here is gamma, below here is alpha plus Fe3C. That's just taken from the phase diagram. If I went back to the phase diagram, you'll notice there is a line right here. Above the line is FCC or gamma. Below the line is alpha plus Fe3C. So let's say that line, it actually says here is 727. So if I go back to my diagram here, and here's the line, let's say this line is 727. So I'm starting up here at 800, I have gamma, I go down to 650 and I make 50% perlite, which is alpha plus Fe3C. So the question was, Ben was asking, what if I went back to 800 degrees? Well, if you go back to 800 degrees, the phase diagram says you should go back to having gamma. So that alpha plus Fe3C that you made would disappear, the perlite will disappear and will become austenite again. So you would have undone what you have done before. Sounds good? And I just again want to be very reassuring. So when you do 2H, that's the course where you would use these concepts the most. You might hear the words perlite, martensite. You now have an idea about them. Perlite is this lamellar structure. It's soft, it's ductile. It looks like it forms here by holding at 700 or 600. You might hear about martensite. Martensite is this strong but brittle structure. The way it forms is by quenching or cooling quickly in water. If they're interested in finding out how much of each phase you have, you now know to look at the phase diagram. So all of these concepts you'll be familiar with, and they do expect that everyone will need a refresher on that. So I'm pretty sure they will go over the concepts and give you more background on them. Does anyone else have a question? Or if you have a follow-up question, Ben, does that help? It's good. Okay, what about other topics? Did anyone want me to go over other topics today? I have one slide that you might find useful. So we talked a lot about phase transformations. I'm not sure how much you talked about mechanical properties, but again, you will probably see the stress-strain curve. So the stress is basically force over area. The strain is the elongation of the sample, how much longer it got, so the change in length over the initial length, so that's the strain. And we very often plot the stress versus the strain. And we get a curve like the one you see here. And the curve has several interesting properties. So typically what you do is you bring a sample. So this is a schematic of the sample. So this here is the grip. This is the machine that's holding the sample in place. The sample is here in the middle, and we're pulling on the sample, and the sample is getting longer and longer. And what you find at the beginning is the stress and the strain are related, or the stress versus strain is a straight line. In other words, sigma is equal to E, a constant, times the strain. That's the equation of a straight line that goes through zero. This constant is called the elastic constant, or sometimes it's called Young's modulus. And it's a material property. And during this initial stage where you have a straight line, we say that the deformation is elastic. It's exactly the same as what you have in a spring. It's basically, this equation is no different from the spring equation, except instead of using force, I'm using force divided by area. Instead of using x, the extension of the spring, I'm dividing the extension by the initial length. And instead of the spring constant, there is the elastic constant, or the Young's modulus. And just like a spring, during this initial part where the sample is deforming linearly, during this elastic part, we call it, the sample is deforming exactly like during this part. Sorry, my drawing is terrible now. During this initial part, I must have a problem with straight lines. During this initial part, the sample is like a spring. If you let go, it shrinks back, much like a spring. So the deformation is reversible, it's recoverable. The interesting event happens around here. When you go past this stress, you notice how the stress strain curve is no longer linear, it's actually now rounded. And the reason is the sample is no longer deforming purely elastically. The sample has now yielded, and we call this sigma y the yield strength. For many materials, the yield strength is what you care about. This is what determines whether the material is useful or not. If you're building a bridge, you don't want the bridge to permanently deform. You want it to be in the elastic part, where maybe if a car or a truck goes in, it deflects a little bit, but the moment it's gone, it goes back. You don't want it to stay permanently deformed. You don't want that. So you want to use the material below its yield strength. What happens if you go past the yield strength is exactly what happens to your spring if you overstretch it. What happens then is the spring recovers part of the deformation, but then part of it is permanent. The spring doesn't go back to exactly the way it was before. It's now overstretched, it's permanently deformed. So that's what's happening in this part of the curve, in this part of the curve over here. So once we go past the yield strength in this part here, the material has a permanent shape change. It's now permanently longer than it used to be. And you notice you need more and more stress to keep deforming the material, because the material is actually getting stronger and stronger as you deform it. The more you deform a material, the more defects will be created in the material, and the stronger the material will become. So that's seen here. This increase in stress reflects the fact that the material is getting harder and harder to deform. And this is called work hardening. The material is getting stronger. It's hardening as we deform it. Now you notice there is a maximum point here, and the reason there is a max and then the stress begins to decrease is the sample begins to neck down, it begins to thin down. So the sample is not getting weaker, it's actually still getting stronger, but we're interested in the force divided by the area, and the force is now getting concentrated over a smaller and smaller area. So the stress can continue to go up, right? Without having to increase the force, you can just make the stress, if the area is shrinking, I don't need to increase the force for the stress to go up, I just need a smaller and smaller area. So what's happening here is just the sample is thinning down, and therefore less and less force is needed to deform it, and finally it breaks over here. So this highest point on the curve is called the tensile strength. And it coincides with the point at which the sample begins to neck down. So before that point, before the point M, for these strains, the deformation was uniform. The sample had a uniform cross-section. It was thinning uniformly and getting longer uniformly. Past this point, you could see this region here was thinning a lot more than the regions up here. So the deformation is no longer uniform. So this strain here is called also the maximum uniform elongation, because beyond it, the deformation is non-uniform. And then the last point we get is this strain here, which is the fracture strain. So it gives us an idea of the ductility of the material. Have you seen that before in 1P10? Okay, so good. So that wasn't a waste of time. Then it was useful. That's good. All right. Okay. Anything else you would like me to touch on? The last topic that Sophie mentioned was directions and planes. I'm happy to go over that. It's not too bad. Do you guys have time? Maybe another 15 minutes? The good news is you will learn everything about planes and directions. You learn it from scratch in 2x. Okay, so let's do that. I mean, others, if you have to leave, it's all right. I'll just take maybe just another, maybe not even 15 minutes, just another 10 minutes to show you the ideas of directions and planes so that you have heard about it before. You see it in 2x in detail. So very often we talk about crystals, and we just need a practical way of telling each other which direction are you talking about in that crystal, or which plane are we referring to. So in fact, there is a convention. There is a way of telling or describing planes and directions inside a crystal. We call it the Miller system. Directions are actually extremely easy because it's no different from what you do in math. So let's take an example here. This direction. If you were doing vectors, I would ask you, what's this vector? And if this is x, y, and z, you would tell me this vector is the 1, 0, 0 vector, right? Well, in materials, we don't call it the 1, 0, 0 vector. We call it the 1, 0, 0 direction. We put it between square brackets, and we don't use any commas. If I took a direction in the negative direction, like this one here, so this one is going in the negative y, in calculus or algebra, you would have said 0, 0, minus 1, and 0. In materials, you would go 0, bar 1, 0. So we don't use negative signs, we use the bar sign. And that's it, there is nothing special. That's it about directions. The same thing here. What's this direction here? It looks like I moved 1 unit in the x, 1 unit in the y, and no units in the z direction. So this direction here is 1, 1, 0. And this last example, I moved 1 unit in the x, 1 in the y, and 1 in the z. So this is 1, 1, 1. And that's it. That's the whole concept of directions. There is one additional rule. If you end up with fractions, let's do that. Just to show the example here. Let's say I started here and I ended up here. X, Y, Z. Did I move at all in the X direction? No. Did I move in the Y direction? Yes, it looks like I moved the full unit in the Y. Did I move in the Z direction? Yes, half a unit in the Z. So our answer cannot have fractions, so what we do is we clear the fractions to get the smallest possible integers. So in this case, I have to multiply by 2, so 0, 2, 1. So the answer is B, 0, 2, 1. So that's the Miller index of this direction. So directions are really easy. The only difference from algebra is no commas, no fractions, and instead of a negative sign, you use bar. And we always put directions in square brackets, exactly as you would have done in algebra. Now let's talk about planes. Planes are a little bit more tricky, but the one thing I want you to remember about planes is the way we describe a plane is by defining its normal. So if I want to know what plane is this one, it's enough for me to tell you what the normal to that plane is. So this procedure I'm about to describe to you is basically just a procedure for finding the normal to a plane. So let's take an example. Let's take this example here, this one here. Step 1 in the process is you have to choose an origin. And you're free to choose any origin you like as long as the plane does not go through that origin. So for example, I can pick 0, 0, 0. This is a point behind the plane. The plane does not go through it, so that's a good point. Am I allowed to choose this point here? Can I pick 1, 0, 0? That wouldn't be allowed because the plane goes through it. Okay? So I'm going to stick with 0, 0, 0 for this example because it's a perfectly good origin that the plane does not go through. Step 2, find the intercepts. So find where this plane intercepts the x, y, and z axis. So where does this plane intercept the x-axis? It touches the x-axis at a value of 1. So 1. Where does it intercept the y-axis? Well, it doesn't look like it intercepts the y-axis. It's actually parallel to the y-axis. It will never touch the y-axis. So the way we say it will never touch the y-axis in math is to say the intercept is infinity. And then the last point, okay, what about the z-intercept? It intersects the z at a value of 1, so I'll put 1 for z. So that was our second step. Our third step is to take the reciprocals of these numbers. So 1 over 1, 1 over infinity, and 1 over 1. So 1 over 1 is 1, 1 over infinity is 0, and 1 over 1 is 1. And then the last step is to clean this up. So if there is a fraction, you get rid of the fraction, and then you write everything without commas and in parentheses, in round brackets. That would be our answer. Sounds good? So let's do an easy example. Let's do this one here. So let's pick a point. That's our origin. Okay, try to do it with me. Try to follow along and do it with me so we can do it together. What's the x-intercept? As before, this is x. This is y. And that's z. So x, y, z. What's the x-intercept? It looks like it's a half, maybe. Okay, I'll put a half. The y-intercept, 1. The z-intercept, 1. What's the next step? You always have to do the steps in order. So the next step is you take the reciprocal. So half becomes 2. 1 stays 1 and 1 stays 1. There are no fractions, there are no negative numbers. I'm all set. The answer is 211. That's my answer. Sounds good? Now notice this example was really easy. But imagine you did not pick the origin as 0, 0, 0. Imagine you said, well, Hatem said any origin will do, so I'm going to pick this origin. Nothing wrong with that origin. The plane doesn't touch it, so you're good. But now you really have to have a lot of imagination to work out what the X, Y, and Z intercepts are. I honestly can't see them. I can see the X is maybe -1. The Y, I'm having a hard time. The Z, I'm having a hard time. So I'm going to quit. I'm not going to continue with that origin. If you start with an origin and it gives you a hard time, don't continue to use it. Pick another origin. And my advice is pick an origin on the opposite side of the plane. So if you tried this origin or this origin and it's giving you a hard time, trying this one will not help. Instead, you would want to try an origin on the opposite side of the plane. So you tried something in front of the plane, it was hard. Try something behind the plane. It will be easy. Are we happy with this? Good? Okay, let's do one more. Let's do, I want half of you. I want the first three people, so initials K, C, S, M, and B, K. Try this origin, and the rest will try this origin, and let's see what answers you'll get. So I'll join the second group, and we're going to try this origin. X, Y, and Z. My intercepts, again, I'm going to just be clear, this is X and this is Y. My X-intercept looks like it's -1. My Y. All right, great. So the three of us who were working with this origin here got bar 1, bar 1, 0. And it looks like the three of you who were working with the other origin, this origin here. So I see here Sarujan. Is that a good, did I pronounce it right? Sarujan got 1, 1, 0. So which one of us is right? We're both right. And the reason we're both right is, remember I said the way we describe a plane is by defining the normal to the plane. But a plane has two normals, the one pointing up and the one pointing down. So in fact, bar 1, bar 1, 0 and 1, 1, 0 are the same plane. If the only difference is multiplying through by -1, it's the same plane we're talking about. Does that help? Are we happy with this? Do you feel confident about planes and directions? So that's it. I think you're all caught up now. You're all good to go. Any other questions, other topics you would like to revisit? All right, thank you everyone. It was my pleasure as well. And I really hope you'll have a great year and you'll stay connected. I know it's a little bit hard. We can't see you face to face. We can't talk to you in class and so on. But really, we're here. We're still here for you. I look forward to hearing from all of you. You don't need an excuse to email me or a reason to reach out. It doesn't matter what course, what topic, what issue you want to discuss. You can always come and talk to me, and I'm very happy to help. I'll do my best to answer questions like these or to help you with any issues you have. And yes, I'll see you in 5 days on Tuesday. We'll have our first 2BO3 lecture, and I'll see you all there.
All right. Thank you, everyone, for participating. And thank you, Dr. Zarab, for taking the time to host the session.
Oh, this was fun. Thanks.
I hope everyone enjoys the rest of their summer. I've attached 2 links in the chat, or not really links, but they're in the names of both of our MSc Instagram page as well as our Society Instagram page. If you're not already following, make sure to follow. You'll get great information on future events and real-time information and live updates. So thanks again for participating, everyone, and enjoy your first year in materials.
All the best, everyone. Thank you, Ben.
Thank you.
Have a good evening.